All right, welcome back. In this video, we are going to talk about information from section 10.6 of AP Calculus BC, comparison tests for convergence. What we're going to do is we're going to introduce you to the direct comparison test for convergence and the limit comparison test for convergence. Two more tools in our toolbox. These two tests are going to be very helpful for us. In the last lesson we talked about P-series, and there are a lot of series that look very much like P-series. They look like they should be a P-series, but they're just not quite a P-series. Well, we can use these comparison tests to determine whether those close but not quite series converge or diverge by comparing them. For instance, if I'm trying to find whether or not the sum from 1 to infinity of 1 over n cubed plus n converges, I can do that. It looks very close, but not quite the same as the sum from 1 to infinity of 1 over n cubed. But by using a comparison test, I can show that these two series have the same kind of convergence behavior. This one's really easy to decide whether it converges, and so by using comparison, we can then decide that maybe this one converges. Okay, so let's introduce you first to the direct comparison test and a few of my thoughts on that. All right. So in direct comparison, what we've got is we've got two series that are greater than 0 for all values of n. We can kind of tinker with that a little bit if we have, like at the when n is 1, maybe one of them is a negative series. We can still kind of get to a comparison, but in general, we want to use this when both a and b are strictly positive, and b here, the series b sub n, is greater than or equal to a sub n for all n. So what's happening is there's two things that can happen when b sub n is greater than or equal to a sub n. If we know that the bigger series converges, if we know that the sum from 1 to infinity of b sub n converges, that's the bigger series converging, then the smaller series is going to converge as well. And in the second case, if we know that the smaller series diverges, that tells us that the bigger series diverges as well. Okay? So let's look at what we're talking about here and what's going on. So we're going to start with a series that we're attempting to decide whether it converges or diverges, and we're going to choose a second series to compare it to. At this point, we have to follow our hunches. What is that second series that we want to compare it to? Well, it's going to look something similar to it, and it's going to be something that we know converges or diverges, or can easily find whether it converges or diverges. On top of that, if I think that the series I'm looking at initially converges, I'm going to try to find something that's bigger than it that converges. If I can find a bigger series that converges, that tells me that the original series converges. On the other hand, if I think that the series I'm looking at diverges, what I'm going to do is I'm going to try and find a smaller series that diverges, because then that smaller series diverging can show that the original series diverged. Now, something that's very important for you to realize here, there are two possibilities that exist that tell us absolutely nothing about the series that we're looking at. If we find a series that's bigger and diverges, that doesn't tell us anything. If we find a series that's smaller and converges, that doesn't tell us anything. All right? I always think about this, kind of as two balloons. The bigger series and the smaller series. We said b sub n was the bigger series and a sub n is the bigger series. If the outer balloon here, the bigger series, blows up, gets bigger and bigger and bigger, what does that tell us about the balloon inside of it? It doesn't tell us anything. So that's why when we have a bigger series that diverges, that tells us nothing about the smaller series. If we know that the smaller series shrinks down to nothing, what does that tell us about the outer balloon? Absolutely nothing. Okay? Whereas the opposite case, the two useful cases are, if the inner balloon blows up, since it's inside the bigger balloon has to blow up as well. If the outer balloon shrinks down to nothing, the inner balloon has to shrink down to nothing as well to stay inside there. And those are these two cases right here. All right. So let's go ahead and we'll look at a few examples of using direct comparison and show you what's going on when we're using this in practice. All right. Here we go. Determine if the following series converge or diverge. We're looking at first the sum from 1 to infinity of 1 over 4 plus 3 to the n. All right. Now this looks very similar to the sum from 1 to infinity of 1 over 3 to the n. Looks very similar. Okay. Now let's see, how does our a sub n here compare to our b sub n here? Well, I know that the fraction on the left, the denominator, is always bigger than the denominator of this fraction. When we have a bigger denominator, that means we have a smaller fraction. So I have that this relationship holds between these two. 1 over 3n is always greater than or equal to 1 over 4 plus 3 to the n, and that is true for all n greater than or equal to 1. So there's our relationship. This is the bigger series. Once we know that this is the bigger series, we're hoping that it converges because then the smaller series will converge. If this series diverges, then we're in trouble. Okay? But this series converges, and I know that pretty easily because it is a geometric series. Geometric. And I like to string these logic trains together when I'm talking about comparison. You know, we show that the one series is bigger than the other. We then figure out, hey, this series converges. Why does it converge? Because it's geometric with r equals 1/3. And the absolute value of 1/3 is less than 1. All right. Since the bigger function, or the bigger series, since the bigger series converges, the smaller series converges. So that tells us that the sum from 1 to infinity of 1 over 4 plus 3 to the n converges. There's our first example. All right. Let's go on to part B. Sum from 2 to infinity of 1 over the square root of n minus 1. This, to me, looks very similar to the sum from 2 to infinity of 1 over the square root of n. So let's compare the two. 1 over the square, oops, I made my square root sign too big there. 1 over the square root of n minus 1, and 1 over the square root of n. Now here the denominator is smaller than this denominator. When the denominator is smaller, that means the fraction is bigger. And this is true for all n values greater than or equal to 2, which is our lower index of our summation. All right, so looking at this, the series that I'm comparing it to is smaller than the series that I'm trying to determine its behavior. So I'm hoping that this is divergent, because if it is, then this bigger series has to be divergent as well. All right, this is equal to the sum from 2 to infinity of 1 over n to the 1/2, which diverges. And why does it diverge? Because it is a p-series. P-series with p less than or equal to 1. Since the smaller series diverges, the bigger series must diverge. So sum from 2 to infinity of 1 over the square root of n minus 1 diverges. Oh, I should have mentioned in the end here the converges. Why do I know this? By the direct comparison test. I should restate what I'm using here. It would also be good here, if I need to know the conditions. I do know that both of these series are positive. Both of these series are positive for all n greater than or equal to wherever the series starts. All right. Part C, we've seen this one before. Looks a lot like the sum from 1 to infinity of 1 over n cubed. And so if I compare these two, bigger denominator, smaller fraction. So that is true for n greater than or equal to 1. Sum from 1 to infinity of 1 over n cubed converges because it's a p-series with p greater than 1. Since the bigger series converges, the smaller series must converge. So, sum from 1 to infinity of 1 over n cubed plus n converges. And here I'm going to use the abbreviation for the first time by the DCT, direct comparison test. You can use DCT, you can spell it out as the direct comparison test. All right, last example here. Sum from 2 to infinity of 1 over n squared minus 3. This looks very much like the sum from 2 to infinity of 1 over n squared. And so we'll compare these two, 1 over n squared minus 3 and 1 over n squared. Smaller denominator, bigger fraction. That's for n greater than or equal to 2. So we're hoping right now that this series converges since it's smaller than the one we're comparing it to. We're hoping it diverges so that the original diverges as well. Unfortunately, this converges because it is a p-series with p greater than 1. Smaller series converges. So DCT is inconclusive. We either need a different series or a different test. I find that in most cases, it's better for us to use a different test. And that's what we're going to talk about in our next video. We're going to talk about that other test, the limit comparison test for convergence. All right, that brings us to the end of this video. We'll see you next time when we talk about the limit comparison test for convergence. See you all then. Have a great rest of your day, and bye-bye for now.